Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Dickry Triandy. I'm from the Electronic Engineering Polytechnic Institute of Surabaya. On this occasion, I will present the result of our research entitled Design and Implementation of Bipolar Sepic-Cuk Converter with Fuzzy Logic Control for Battery Charging Application. This research was assisted by my supervisor, Mr. Endro Wahjono and Mr. Farid Murdianto. Introduction. A solar cell is a power plant capable of converting sunlight into electric current. Solar cell can be used to supply a system including housing, transportation, electronic device, and used for charging batteries. Problems that arise from the use of solar cells where the amount of electrical energy generated depends on the intensity of light and temperature, thus making the power output to the system vulnerable to instability. Therefore, we need a system can store energy properly. A bipolar DC microgrid system is that it can minimize power loss. If there is an interference in one line, the other lines will continue to operate. Bipolar converters produce the same two output voltage with two different polarity, able to charge faster in quantity, where one converter can charge two batteries at once. System design. The following is the design of a system that has been carried out in this research. There is a solar cell. I use a solar cell with specification 2 by 100 watt peak with a parallel configuration, producing an output voltage of 17.5 volt. Then the output voltage from the solar cell will be input for bipolar converter, the Sepic converter and Cuk converter. The output of the converter produces a voltage of 13.8 volt which is used for the battery charging process. The control used is the fuzzy logic controller. By adjusting the duty cycle converter, which is adjusted to change in the performance of the solar cell and the voltage for charging the battery. Modeling of fuzzy. The general structure for fuzzy logic-based controller is shown in block diagram. There are two inputs, one is the error and the other is the delta error, compared to the reference voltage, and one output that determines the mode of operation of the battery. The fuzzy logic controller has three main components: fuzzification, fuzzy inference system, and the fuzzification. Fuzzification is the first stage of the fuzzy inference process. At this stage, the input data is received and the system determines the value of its membership function and convert numerical variable into linguistic variables. Membership function give meaning or define linguistic expression to be number that can be manipulated. Fuzzification obtains a value and combines it with the membership function to produce a fuzzy value. Fuzzification is the process of determining an input number for each fuzzy group. The fuzzy inference system is used to map input value to output value using fuzzy logic. Inferencing or rule-based, fuzzy rules are generally expressed in the form of if-then, which is the essence of fuzzy relation. The fuzzification is the process of converting fuzzy data into numerical data that can be sent to the control equipment. Design of fuzzy. At the fuzzification stage, we determine the membership function input variable error and the membership function input variable data error. The error range and the data error range are obtained from the open loop converter simulation. We are using 7 triangular membership function. Furthermore, after the fuzzification process, namely determining the rule base, using a 7 by 7 formation, then define the membership function output here. In this paper, we use 7 triangular membership function for reference error and 7 triangular membership function for change in delta error. Therefore, 7 by 7 or 49 rule base are used to design a fuzzy inference system. Linguistic variables are defined as ND, NM, NS, Z, TS, TM, and TB, which mean large negative, moderate negative, small negative, zero, small positive, moderate positive, and large positive. Fuzzy rules are summarized in table. Fuzzy interface machine type is Wahjono. Design of membership function output. There are ND 0.35, NM 0.4, NS 0.45, Z 0.5, TS 0.53, TM 0.54, and TB 0.57. From the rule base and membership function output, we get the surface. Simulation circuit. In this simulation, we use fuzzy control that are by design, using two parallel solar cell and bipolar converter, Sepic converter and CUK converter. Simulation result. From the graphic, the simulation is given a disturbance on the irradiance side. The result is that the control function properly where the output voltage when given a disturbance will return to steady according to the voltage set point. The disturbance is given in seconds 0, 0.2, 0.4, 0.6, 0.8, and 1. By adjusting the irradiance 500, 200, 500, 200, 500, and 1000, the output voltage response when using the control produces a stable voltage when disturbed. Furthermore, from the graphic, the simulation is given a disturbance on the temperature side. The result is that the control function properly where the output voltage when given a disturbance will return to steady according to the voltage set point. The disturbance is given in seconds 0, 0.2, 0.4, 0.6, 0.8, and 1. By adjusting the temperature 30, 25, 40, 25, 50, and 35, the output voltage response when using the control produces a stable voltage when disturbed. Conclusion. Table 1 and Table 2, the Bipolar Sepic-Cuk Converter simulation result are obtained using fuzzy control, where the simulation is given interference on the irradiance and temperature side. Table 1 shows the simulation result with three different conditions by changing irradiance. It produces static voltage output of 13.82 and 13.85 volt, while for CUK it is negative 13.82 and negative 13.85, with an average error of 0.14 to 0.36%. Table 2 shows the simulation result with three different conditions by changing the temperature. It produces static output voltage is 13.85, 13.86, and 13.87 volt, while for CUK voltage is negative 13.85, negative 13.86, and negative 13.87, with an average error of 0.36 to 0.5%. Simulation result. The graphics show the output voltage response of the PI control and fuzzy control. The result obtained after running the simulation are the CUK output voltage is negative 13.86 volt and the Sepic output voltage is 13.82 volt for PI control. And the result obtained after running the simulation are the CUK output voltage is negative 13.81 volt and the Sepic output voltage is 13.81 volt for fuzzy control. With change in radiance from 900, 500, 900, 200, 800, and 1000, the converter output voltage remains stable and returns to the set point voltage. Conclusion. From the table, the output response parameter from PI control and fuzzy control. It can be concluded that the time needed to reach the set point using the PI control for the safety converter is 0.18 seconds, and for the CUK converter is 0.164 seconds. While using fuzzy control, the time needed to reach the set point for the safety converter is 0.048 seconds, and for the CUK converter is 0.061 seconds. That is all from me. I would like to thank you for your time and attention. I'd like to apologize if there is a mistake. I hope you have a nice day. Assalamualaikum warahmatullahi wabarakatuh.